Thank you for the opportunity to inform CISREP about the Everglades Vulnerability Analysis, or EVA for short. I'm Laura Diacunto, an ecologist at USGS and the scientist leading this effort. A team of scientists from both the USGS and National Park Service work on this project, and I have listed the full team here on this slide. If you have any questions or feedback for me, please feel free to email me at ldiacunto@usgs.gov. And I'll be happy to get back to you as soon as I can. As projects authorized in the SERP are built and begin to come online, modeling is used extensively to assess the potential impact of these projects on the ecosystem. Typically, the outputs of each of these models cannot be compared easily because they are using different modeling frameworks. The outputs are in different units. They cover different spatial extents, or they may be operating on different temporal scales. Additionally, uncertainty within the models is either unavailable or is not considered when comparing across scenarios using these models, which can make choosing between alternative plans more difficult. In Recover's 5-year plan for 2017 to 2021, a call for a vulnerability analysis was made. Recover recognized the need to integrate models and knowledge of the Everglades system into a common framework in order to identify the areas and parts of the system that may need attention as restoration and climate change progress through time. Our team has been working with Recover for 3 years to develop such a framework, which we now call the Everglades Vulnerability Analysis. So given this context, the overarching objectives of the EVA include the development of a modeling framework that can predict the responses of the Everglades ecosystem. Specifically, the framework needs to have the flexibility to utilize data from different sources, such as monitoring, experimental, and expert knowledge, so that it can incorporate the full breadth of knowledge available in the system. Second, the framework needs to be able to incorporate connectivity between different parts of the system. And third, we wanted this framework to be able to be easily updated with new data and understanding as monitoring or new scientific knowledge becomes available. A second objective of this project is to build the capacity for Recover and other Everglades restoration stakeholders to better understand uncertainty in the system and utilize it as part of their assessment or decision-making processes. So the EVA as a modeling framework works in the following way. First, we have model inputs, which currently include hydrologic information calculated from daily water depths. Currently, EVA has the flexibility to take South Florida Water Management District Regional Simulation Model Hydrology, Everglades Depth Estimation Network Hydrology, or USGS bisect hydrology. We also include as inputs daily pore water salinity and other landscape level predictors, such as distance to the coastline. The inputs are then translated to the model outputs, which are the responses of Everglades ecosystem health indicators. Currently, we have worked 4 different indicators into EVA. EVA can predict the probability of vegetation type on the landscape, the probability of sawgrass peat accretion or subsidence, the probability of alligator nest presence, and the probability of different sizes of wading bird colonies. Then these outputs are translated into a surface of relative vulnerability for each indicator by calculating their distance from a user-defined ideal state. In the next few slides, I will briefly explain the methodology that brings us to each of these outputs. So EVA is a series of connected Bayesian belief networks. Each indicator is modeled through a Bayesian network we define as a module, and each of these is connected to the other modules in various ways when it makes ecological sense. We first generate an influence diagram for each module. And in this example, the vegetation type is influenced by various hydrologic, salinity, and landscape variables. Each circle or node on the influence diagram is then discretized into categorical bins of outcomes. Using the literature and trial and error, we try to find the categorizations that allow us to differentiate between the outcomes as best we can. Then each discretized circle or node on the influence diagram is related to the ones it is connected to through conditional probability tables. The conditional probability tables describe the relationships within the network and can be learned through various algorithms using observational data, or can be defined by modelers using expert knowledge or experimental data. We can then use the model inputs to run the network through to generate spatially explicit outputs and their associated levels of uncertainty. The example here shows predicted vegetation types for a year using bisect modeled hydrology and salinity, and the associated uncertainty level in the bottom pane. So darker blues in the bottom pane are areas of greater certainty within the network. Finally, we assess the accuracy of model predictions through tenfold cross-validation simulations and assess how well the model is doing at predicting our outcomes, assuming it is a network where we have monitoring data to assess it with. So in this example, we still have some work to do with predicting pine rockland, red mangrove shrub, and open water types, but this process is completed iteratively in order to settle on the best possible network given our data constraints. So once we have a network we are happy with, we can start to translate these outputs to vulnerability. I'll illustrate how we do this with the sawgrass peat accretion network as an example. To translate this into vulnerability, we take the predicted probabilities of sawgrass peat accretion and then define an ideal state that incorporates some amount of uncertainty. Since we do not want our sites to experience areas of peat subsidence or collapse, our ideal state would rest in these two categories where subsidence is close to zero or is positive, meaning the peat is increasing in that cell in the landscape. We can then conduct an ordination process using a principal components analysis, or PCA, to collapse all sites into a two-dimensional space, all site variables into a two-dimensional space. The distance between our idealized sites and the predicted outcomes becomes our measure of relative vulnerability. So the greater the distance from an ideal site, the more vulnerable it is. We can standardize these distances on a 0 to 1 scale in order to produce consistency when comparing across restoration scenarios. The modules are currently connected in various ways, and this figure shows how those connections play out when running AVA. The biggest takeaway here is that we have currently built the capacity to use the output of the sawgrass peat module to adjust the elevation within the model and subsequently impact the water depths for the next annual iteration, effectively connecting all of the networks to each other through this process. In the next two slides, I'll illustrate what we can do with AVA to help with different restoration questions. First, we can use the output of the vegetation module to explore how vegetation succession may change as sea level changes. In this figure, we took a brute force method to sea level change and used the core sea level change calculator, increasing depths along the coast according to a bathtub model of inundation, which is not the way we would want to go with producing sea level change scenarios for a formal analysis, but this was just the way that we were able to do it currently. This graphic shows 3 years of output from left to right for the years 2000, 2009, and 2017. The top row are predictions using current bisect modeled hydrology and salinity, while the bottom row are predictions using bisect using the high sea level change scenario. Mangrove, which is the orange color, is moving further into the coast as time goes on in both scenarios, but the high sea level change scenario, the bottom row, also reveals more open water along the coast than in current conditions. Next, we can also look at sawgrass peat vulnerability over the same time frame and sea level change scenarios. So just a reminder, the columns are the years 2000, 2009, and 2017 from left to right. The top row is bisect modeled current conditions, and the bottom row is the high sea level rise change or high sea level change scenario. One thing to remember with this is that the peat module currently only looks at sawgrass peat. So once sawgrass disappears from the landscape, it is no longer there to be vulnerable. So while it looks like the intermediate, while it looks like the high conditions scenario is more vulnerable, this is likely because sawgrass has been replaced by open water or mangrove in the high scenario, as opposed to the current conditions. scenario. So we have a couple of things planned in the next year that will improve AVA and get it ready to start helping with Everglades restoration decisions and planning. First, we've been asked by the Corps to expand our list of vegetation types, adding things such as cypress and cattails, and we'll be working on incorporating those changes this year. We're also working on incorporating mangrove peat into the peat dynamics module to increase the utility of coastal vulnerability and to perhaps address the issue of some peat disappearing from the landscape as time goes on and making our assessments of vulnerability a little wonky in some of the scenarios. Finally, we're running sensitivity analyses to understand how AVA responds to changes in the inputs, how ideal states are defined, and the sample size of ideal states simulated so that we can identify best practices when using the tool for a decision process. Thank you so much for listening, and feel free to reach out with anything else you may need from our team. Thank you very much.